Thank you so much for listening. Today, myself, Ryan Acton, and my group partner, Hayden Norrie, will be discussing our thesis work, which is on a comparative evaluation of walking methods for reducing simulator sickness for a high-fidelity archery virtual reality simulation.
When we began this research, we asked ourselves, why this question? And we found that there are a few reasons why this research is important.
With the decreased prices of consumer-grade GPUs, low-fidelity simulations, and cheaper equipment, such as the Oculus Quest 2, VR is becoming much more accessible. Additionally, people are finding more societal benefits that come from VR, such as autism intervention, phobia therapy, pain reduction in burn victims, and driving training.
In order to understand our research, we should define what simulated sickness is. When a user experiences simulated sickness, they often experience symptoms such as nausea, headaches, and dizziness, and other symptoms. It's similar to that of motion sickness. We based this on something called the sensory conflict theory that states that if stimuli from the outside environment are being perceived differently by human senses, as often is the case with virtual reality, you will experience simulated sickness.
Locomotion is the ability to move from one place to another in physical space. The virtual reality locomotion is the technology that enables movement of the avatar or user through the entire virtual world using only a small real-world space. We know that this locomotion induces simulator sickness.
Thus, we had certain objectives of this research. So, given that we know that locomotion induces simulated sickness, we set the following objectives. We wanted to design a novel method, a locomotion method known as the Cradle Method, and its use of haptic feedback that will reduce simulated sickness of a user, increase its performance, and would compare this to currently used locomotion methods.
Before we start, there are a few things we need to understand.
Simulated sickness can be triggered by a few things, namely field of view, virtual environment realism, vection, and individual factors of humans, such as age and gender. We also need to know how to measure simulated sickness. We use questionnaires, which are subjective, like a SSQ, the Simulated Sickness Questionnaire, and other measures that are objective, like physiological measures, such as heart rate.
Given the project aim of evaluating simulator sickness for different locomotion methods, the virtual environment that our participants will traverse should be designed in such a way that it will induce a base level of simulator sickness from which we can make comparisons. We did this using the forest, which increases vection or illusory self-motion, uneven ground, increased realism, and randomly appearing targets that force the user to look around in the environment.
This is the resulting Robin Hood environment terrain that we designed.
Here you can see examples of some of the mechanics included, such as the bow, the targets that are placed on the trees, and the hands that you can see. If you'll notice that there is an arrow on the floor that points in the direction of the nearest target, once a target has been fired at and hit successfully, it will disappear and a new target will appear, which the arrow will then point to.
Given our objectives, we had to design something called the cradle. The cradle is simply a ring to attach to the walls via tether cables and surrounds a user. When a user walks into the ring, they'll move in the virtual environment in the direction that the ring is being pushed. This was done using ring displacement and three-dimensional vector subcomponents.
Here you see the final cradle design. That is a plastic ring that is reinforced by hula hoops on the inside. The ring itself is supported by 6 elastic bungee cords. Here you see a demonstration of the arm swinging method within our developed virtual environment. The user will move in the direction their head is pointing, and their movement speed will be determined by the extent to which they swing their arms. So for instance, smaller arm swinging motion will result in slower speed, and greater motion will result in increased speed in the virtual environment.
Here you can find a
Here you see a demonstration.
Here you can find an example of the teleportation method where a user points in a direction, clicks a button on the remote, and they will appear in the environment where they are pointing.
Here you see a demonstration of the cradle locomotion method. For this method, the user moves in the direction that they displace the cradle, and the extent to which they displace the cradle has an effect on the speed. For instance, pushing harder on the cradle and pushing it further will result in an increased speed, while only pushing a small amount will result in slower speed. This is calculated using the HTC Vive tracker attached, which acts as the origin points, and then displacement in the X and Y planes is used to figure out which direction the user is moving.
To determine if our cradle was effective in reducing simulated sickness, we had to invite users to play the game and try each individual walking method. We thus conducted a single factor repeated measures ANOVA test.
We know that from previous research, certain factors affect simulator sickness. Thus, it is important to specify an inclusion criteria to be followed for the recruitment of the participants in the experiment. They must be a university student to allow for easy access to campus. They must be Cape Town based to meet the same requirements. They must be neurotypical, and they must have no comorbidities to ensure no COVID-19 dangers, and they must be between 18 and 30 years of age.
For this experiment, we measured simulated sickness using an SSQ and performance using a target hit ratio, which was simply the number of successful target hits over the total amount of targets shot.
The experiment procedure was as follows. Phase 1 involved the hardware preparation, which include resetting and sanitizing everything. Phase 2 involved explaining the experiment process to the participant, as well as the risks involved, and so that the participant can give their informed consent to participate in the research. Phase 3 involved the task evaluation and execution, in which the order of the experiments was randomized. The participant began the first experiment, filled out the SSQ and GEQ, and then repeated this process for the remaining experiments. Finally, phase 4 involved paying the participant for participating in the research and allowing them to give any oral feedback they might have.
Through our trials, we found there was a statistically significant difference between the shot accuracy scores of each walking method, and we can see that the cradle actually reduced performance rather than increased performance.
In terms of the simulator sickness results, there was no statistically significant difference between the nausea, oculomotor, and disorientation scores for the walking methods. Combined, this meant that there was no statistical significant difference found between the simulator sickness scores for each respective walking method.
Finally, we conclude that there's no significant decrease in simulated sickness and may be due to a low sample size of participants tested. Thus, we warrant further investigation because of the Cradle's competitive scores. We also measured game experience and we found a little distinction between each method, and we found that the Cradle produced the lowest accuracy scores, possibly due to an unfamiliar continuous motion.